All right, what's up, party people? This is Mr. Shorman talking about how to do a beam deflection static stress analysis in Fusion. So what I've got loaded up for you here is two separate beams. One of them is just a plain rectangular beam, and one of them is an I-beam. Both of them I have chosen, if I go right-click Properties, I have chosen to model them as aluminum. In Fusion you can change the property. You can make it aluminum, steel, wood, plastic, MDF, whatever you want to make it. And now I'm going to show you, once you've made it, how to actually test it. So while for some of these simple shapes we might be able to use a beam deflection calculation, there's going to be more complex shapes in real life, and what Fusion can do for us is provide a simulation where it actually creates a physics environment where it puts these forces on these modeled pieces and says, hey, here's what's going to happen in a more realistic environment. And so here's how we do that. First, we need to actually get out of the design workspace. So we do that by clicking here and going to the Simulation Workspace, which is totally different. And then Fusion can do a lot of different simulations. What we're going to look at is a static stress, because this is a static, this is a beam, this is a structure. We don't want it to be moving, so it is static. And stress, we're going to see what happens when we put various forces on it. So I'm going to click Create. And then, because I'm in a new workspace, all my options have changed. So what's really, really important, what you have to do, is you have to give it loads and you have to give it constraints. You have to tell the computer, well, what forces are acting on my beams, and you have to tell it, how are my beams constrained? Where are they fixed? So the most simplest thing we're going to do first is we're going to add constraints. So I can click on this constraints icon here that has the little triangle in the circle, or I can click the drop down and select structural constraints. And just like something like a joint in an assembly, we have different kinds of constraints. The simplest ones, and what I'm going to use today, are called fixed constraints. And so when I have this selected and then target selected, anything I click, I'm telling Fusion, hey, this can't move. So if I'm saying this is a beam, let's say, supported at both ends, well, I'm going to say the very end of the beam, and I'm going to click here, can't move. I'm saying that line that I have highlighted can't move. I could select the face, I could select a different line. There's a lot of different things I could select to say, well, don't move, depending on how I want to simulate it being supported. I'm going to, on both of my beams, I'm going to select the bottom edge of the left side. I'm going to zoom out and rotate around, and the bottom edge of the right side. So I'm saying that all four edges are fixed. It can't move. I'm going to say OK. So the first thing I have to tell it is a constraint. I also have to tell it a load, how much force is on it and where. So I'm going to show you a few different ways we can do it. I'm going to click this structural loads icon here. So the default selection is a force. Force is kind of interesting. If I click, say, the top, let's say the top of this beam, this is maybe some kind of floor joist, is experiencing a force. If I click on it, you'll see the default behavior, all these arrows are spread out, is a distributed force. That is one of the things we have equations for, so we might model something as a distributed force, say if there was a load all along this beam. We also might model it as a point force, and there's a few ways to do that. I could change to angle, and now I only have one blue arrow, and I can angle it, and I've got these different rotatable, grabbable handles to change how it's angled. Or, I'll switch back here just to reset that. You can do vector. Vector is pretty nice because if I give it, it's giving me red, and I'll show you why. I can say, well, where it is from the center of this face, and I can give it a limit target. I can basically make a circle that I can make bigger or smaller that is the circle on which this force is acting. So this would allow me to give more of a point load, but maybe a little bit more accurate, as I could say, well, it's not really acting exactly on point, it's acting in a circle. What I'm actually going to do first, though, I'm going to cancel that. I'm going to not do force, I'm going to do a remote force. You'll see there are a lot of options, pressure, moment, there's a lot of them. I'm going to do remote force. Remote force is really nice. Target, I'll still say that top face. Because, it's got these sliders I can drag, so if I'm saying, hey, there's a force at the end, or there's a force that I know is exactly 275 millimeters, or wherever, I can drag it and put it exactly where I need it to be. So I'm going to forget about that, I'm going to cancel out, and I'll just do a remote force on this target. Now right now it's right in the middle, 457 millimeters. Magnitude, How much force is there? I'll say, I don't know, 10,000 newtons, 10 kilonewtons, a lot of force. I'm going to say okay. And now there's this blue arrow and all these little lines. I'm going to add another force to this one. We're going to go load. We're going to go force. We're going to go force this time. And we're going to say 10,000 newtons again. You can also change units, newtons, force, whatever you want. We'll say newtons. And this, if you hover over it, you see that it's a pressure. This is all acting in this one point, and it's being spread out. So different ways of modeling a force. So this is a 10,000 Newton distributed force. This is 10,000 Newton point force. We'll see if those behave the same or differently. So I've added my constraints. I've added my load. That's the biggest thing. Now up here, there's this little pre-check. If it's red, it means the study cannot be solved. If it's orange, it means there's something you might want to check. And if it's green, it means good to go. If you click on this, now there's a lot of stuff going on here. First, DOF, degrees of freedom. If I click this, it'll pull it up, and this is a view potentially fixed. It's worried that I have under-constrained these beams. It wants me to add more constraints. I'm going to ignore that for now. Similarly, this is in this display degree of freedom view. If I pre-check it, the other errors have to do with contact. Basically, because I have two bodies in here, it's like, hey, are these bodies touching? Should you worry about these bodies be touching? Since I'm doing vertical forces, I'm not worried about these bodies touching. So I'm going to ignore all these warnings. I'm going to go to solve, and I'm going to click solve. Now, it takes kind of a while to solve because it takes credits. Now, because we're education, we have free credits, but I'm going to click solve. And usually it stays as a little pop-up. But it takes a while to solve. Here you go. And I will probably edit the video and edit this out because it could take multiple minutes because this is a simulation. It uses a lot of computing power. So you are actually basically asking Autodesk to use one of their computers to solve this for you. And then you're waiting in line. So I will wait here and I'll edit the video magic maybe, and you'll hear from me again when it's solved. Okay, so now we're back. The simulation is complete. So I'm going to click close. It shows me up here a little pop-up that it's complete, and then I can look at my results. My results are up here. So if I click results, it'll take a moment, but not as long as the actual simulation usually. We'll see. Drink some water while I wait. Okay, there we go. So a lot of stuff pops up. First, something I'm going to do is they try to do this thing that's nice. They call it guided results, where they're telling you stuff about it, which is interesting, but I'm actually going to ignore that. I'm going to just go to results just to get that window out of the way. And in fact, this window's maybe in my way. I'm going to hide my data panel too. There we go. I got a little more room. First thing you'll notice, both of these beams are deflecting, it seems, quite a bit. One thing to point out is that this deformation, so the default behavior is what they call adjusted deformation, that they actually really blow up, they really magnify the amount that it deforms so you can see it. Because in a lot of real things, they'll be deforming millimeters. You won't really see it in the model, but you want to know about it. So you'll look at it like, oh, it's right there in the middle. That's where it deforms a lot, which makes sense. If you click actual, you'll see, these snap back. And if I go to a right view, you can barely tell. Now, if I zoom way, 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 way in, you can see that green line is where the top was, and that blue line is where it is. So it did deform this much, whereas undeformed would show it as it was modeled. So it's not actually going to visually show you any deformation that happens. But I'll go back to adjusted so we can really see it. It really exaggerates it. We can go to 5 times if we really wanted to see it crazy exaggerated. A few things that I then think are interesting. One is look, this I-beam is deforming way, 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 way more than the solid beam. Again, adjusted. And there's really 2 reasons for that. One reason is that this is a point force, so all the force is in the middle, where this is a distributed force, and some of the force is at the ends. And this stuff at the end is not going to deform as much because it's closer to our support. That's reason 1. Reason 2 is that cross-section, that area moment of inertia. This is an I-beam. This is a rectangular beam with the same overall dimension. So because this has some extra stuff here, it'll have a little bit better moment of inertia. But honestly, most of it is due to the distributed force versus the point force. Other things you can look at, things that you might want to be able to see. So this default is safety factor. A factor of safety is a multiplier of, maximum, minimum, how much you want this thing to not break. And so this is all blue. Their default behavior is, near 8 times the amount of force versus how this aluminum will break. You're 8 times away. 7 times away is the minimum. So this aluminum is never, ever, ever coming close to breaking under these loads. This 2 means double, means you're double the safe limit, which sounds like a lot, but that's what we call a factor of safety. So you'd want to live here in the green lane range in real life. But I'm like, I'm not worried about designing this for manufacture. I want to know how much it will deflect. Well, some cool stuff you can see over here in displacement. If I go down displacement and I click, say, total, it'll show me. And again, I could visibly see that this was displacing the most and this less. And I can obviously see that the middle is displacing more than the ends. But let's say like Z displacement. What's really nice is there's a few things I can do. I can see that, okay, my slider, red is 0.001. So the tops of this are actually going up 0.01. I guess just because we fixed the bottom and so it kind of bends up is what they're showing me. But then say the bottom here, it deflects 0.639 and I'm in millimeters here. So almost a millimeter, which is kind of a lot. Obviously now, if you saw a half a millimeter in real life, you wouldn't say, well, that's not really that much at all. But relative to what we're doing, that's where it deflects the most. Other things I can see is inspect this min-max probes. This can be really nice. Since I'm on deflection, it shows me. Here's where the max deflection is. It's 0.001 millimeters. Here are the exact XYZ coordinates. Same thing with the min. Now, an interesting thing is because I have 2 bodies in the same study, you won't always do it this way. You might do 2 separate studies with 2 separate designs. The min is on this. It's not going to, by default, show me the min on this. One thing I can do, come over here, go to Model Components, Bodies, and Body 1, I can hide and isolate, and then I'll get the info for body 2. So body 2 is deflecting 0.43 millimeters. So that's some cool stuff we can see is with the deflection here. Other stuff we might want to see is the stress. If we click on the von Mises stress, we see that the most stress is right there in the middle. But there's also, if we zoom in, a lot of stress here because all of the deflection and reaction is happening there. That might be a little interesting. We might be talking about stress. That'll be in here. We might talk about reaction forces. If I want to know, say, the Z reaction forces, there we go. They're happening here. And I think it's kind of interesting because it's 3,600. Now you might say, oh, well, Mr. Shortman, we put a 10,000 Newton force on there. Shouldn't it be 5,000 on each side? But you can see it's actually distributed. And I bet if you found some way to integrate and add up all these colored regions, these would each end up to about 5,000 Newtons on each side. You can see strain. If we're caring about stress, strain, shear, we might care about these things. And contact force. If you have 2 bodies in a model that are actually assembled that are touching each other, the contact force, them pushing on each other, might be in here. So all these stuff can be found in here. Most common things you and I are going to be looking at in my class, we're going to be looking at reaction forces and displacements most commonly. And that's how we do it. And then you click finish and you leave the results and you're back at your simulation workspace. And if you'd like, go back to design